Hello, I'm going to give you an example today, related rates on a area of a triangle, but not the area we're used to in geometry, the 1/2 base times height. The reason why is because when I look at this triangle, I can't for sure find the height without doing some trig first, because I don't have a segment that's perpendicular to another segment. So we're going to go back to our pre-calc course and recall a formula for area of a triangle when you're not given a perpendicular segment. And that formula is 1/2 AB sine C. All right, maybe we remember it, maybe we don't, but let's put that into our notes so that we can recall it if asked to do so later. All right, the problem says we have two sides of a triangle are 4 and 5 in length, and the angle between them is increasing at a rate of 0.06 radians per second. So first of all, what I want to stop anyone from thinking, because my initial thought was, oh, the other side's 3, is the idea that this is not a right triangle. So I know we're used to the 3, 4, 5 triangle. We've used it a lot in our math courses, but that only works if this is a right triangle. So please don't think that this side over here is 3 units long. All right. Then we need to say what is going on with our problem. So we've got increasing rate 0.06 radians per second. What is that? Well, it's a rate, so it's a derivative, right? Our angle is increasing, so it's the derivative of our angle. We're going to call our angle theta. And it's happening radians per second, so therefore it's our derivative of our theta with respect to time. It's increasing, so we know it's positive, 0.06 radians per second. Okay? Find the rate at which the area of the triangle is increasing. So rate of the area, and it's increasing. So we're looking for the derivative of our area with respect to time. We know it's increasing, so right away we should know that we're going to end up with a positive answer. Okay, so we're looking for that when we know theta is pi thirds. When the angle between the sides of fixed length is pi thirds. All right, so let's adjust our formula. First of all, I'm just going to change this C to a theta. And then since I have fixed sides A and B, I'm going to put those in. So my area is equal to 1/2 4 times 5 times sine of theta. Simplify it a little bit. 1/2 4 times 5 is the same thing as 10 sine theta. And now because we need to find dA dt, we should be thinking, oh, okay, I need to take the derivative. So I take the derivative of this function, so dA with respect to time. So you're first going to take the derivative with respect to theta. So the derivative of 10 sine theta is going to be 10 cosine theta. And then you're going to take the derivative of theta with respect to t. So you multiply it by d theta dt. Next, we plug in what we know. So we know that our theta is pi thirds, and our d theta dt was 0.06. Okay, and now we have to go back to our trig exact values. Some of you might know what cosine of pi over 3 is right away. Great. That's what we need you to be able to do. Some of you might need to take a refresher on exact values. Let's just do that so I know where that's at. Pi over 3 is the same thing as a 60-degree angle. So some of you that aren't as comfortable with radians are a little bit more comfortable with degrees. 60-degree angles. If I drop down my triangle, opposite 60 I know is root 3 over 2. Adjacent to 60 is 1/2, and my hypotenuse is 1. So if I look at cosine of pi over 3, I am looking at 1/2. So dA dt is equal to 10 times 1/2 times 0.06. And then 10 times 1/2 times 0.06 is 5 times 0.06, which is 0.3. Let's make sure we put some units on this. Since it's area, we should know that our units need to be squared. So our units were initially meters. Okay, so now our units for our area are meters squared per second. You could also get the units from the idea that this is meters and this is meters per second. So if you multiply meters by meters per second, you end up with meters squared per second. And that concludes our problem.